Now we start our chapter 4, laminar boundary layer. So in this chapter, we will discuss about application of what we learned in chapter 1 to 3. In chapter 1 to 3, we are focusing about the viscosity and so on. So and then we calculate from the Navier-Stokes equation or any methods to know the velocity profile. So and then so means that after we could get the velocity profile, so we could calculate the pressure, and sometimes we could calculate the shear stress. So and then in chapter 1 to 3, we found that we neglect the idea of shear stress. So means that we assume that the flow is very smooth, okay, it not give any resistance. Okay, but in reality, so because the existence of velocity profile and so on, so in reality, the resistance of fluid itself is very big, it's very high, because fluid has shear stress, it could create resistance. It could give us a unique phenomenon that's called lift and drag force, actually. Okay, now we start with the idea of lift and drag force. For example, if we have one object, because we want to talk about the lift force also, so means that I bring you example of an aerofoil here. So for example, if we have aerofoil here, so we have a flow from left to right, and then we show as capital U here. So it will produce lift force, which is vertical direction here, and it will create drag force in the horizontal direction there. So in simply idea, so lift force is actually perpendicular to the airflow, and the drag force is a force that acts parallel to the airflow. That's why in our calculation later on, so we will found that the drag force is actually the summation of force in x axis, and lift force is the summation of force on y axis. Okay, let's say we have one small area here. So and then we write as dA. So and then we have one free stream velocity, for example, an airflow from left to right. So we mention as capital U. And then what we could say that it will give us two type of force. One, because when the flow goes up and goes down like this, it will change the velocity. So if the velocity is changed, means that the pressure also change. So when pressure change, or when pressure act on the surface of this one, so it will create force. So mean first we could say that there are force due to the existence of the pressure. And then the second one is we learn about the no slip condition, the shear stress and so on and so forth. So means that the shear stress there will give us another type of force. So this is a common equation. We could calculate the force by multiplying the shear stress and the total area. So we have force from the pressure, so and then we have force from the shear force. So and then if we want to define this equation, mean the summation of force on x and y direction, so means we need to get the component force in x and y. So for example, if we have a force here with P times A, so we could have the x and y component as shown here, and then the force comes from the shear stress will give us component of this one. So and then so if we do the calculation, we try to construct the equation for drag force. We could say that the summation of x direction forces can become like this one, P cos theta dA and tau sin theta dA. Okay, so and then this is the terms for the lift force, P sine theta dA and tau cos theta dA. Okay, the problem here is in this equation, so we could measure the value of pressure. So the simple one is by using the pitot tube. Okay, so or we could use the U-tube manometer and so on. So that is very common pressure measurement. So we could calculate the d sine theta or cos theta. We could calculate the value of A, means the value of area. But we have some difficulties in terms of measuring the value of shear stress, because shear stress is very unique, so we cannot put any device to on it. Okay, the problem actually same with the idea of Navier-Stokes when Navier give term of shear stress. So and then the Stokes try to measure or try to calculate the shear stress by using the idea of viscosity. So again here, we cannot just straightforward to calculate the lift force and the drag force because we don't know the value of shear stress. However, because shear stress here will lead us to the idea of velocity distribution, so we will found that there is a unique idea to measure the lift force and drag force by the idea of boundary layer. So later on I will discuss about boundary layer. So we go for these notes first. Okay. So and then the comparison of actual drag force and the calculated drag force. In the beginning of this research, we found that there are no similarity. So what researchers do is researcher will add and a coefficient on the equation. So I think this is the common equation that you already know to calculate the drag force and the lift force. So the FD is equal to CD times 1 over 2 rho AU square, and lift force is equal to 1 over 2 CL 1 over 2 rho AU square. So the CD is the drag coefficient and the CL is the lift coefficient. So this idea equation actually can be calculated or can be proved by the idea of similarity. Okay. So however, we must be very careful with the parameter of A here because it change according to the condition and definition. So means that if you do research in aerofoil or in for any objects, so you must make sure that you will get a correct definition for the area. So for example, so if we have a falling sphere like this one, if we calculate, we could get that the drag coefficient is around 0.5 and the area is actually the projection area. So we not take the surface area of sphere in the calculation. Okay, we just take the projection area. So I think you know the projection area means that if we have a torchlight here, so the sphere will give us the circular shadow. So this circular shadow is called the projection area. So and then if we have a falling cylinder like this, the drag coefficient is 0.8 for this situation, and this is the area. But the same cylinder will give us drag coefficient 1.1 if we put like this, and then the area will become this rectangular area. So again means that sometimes we need to very specific about the cross-sectional area that are involved in the calculation. So this is the situation for the force that occur when you have an object when the flow around a certain blunt body. So one of them is called a drag force, one of them is a skin friction force. Okay, so what is the difference? So the difference is the drag force here is actually due to the surface that perpendicular resists the flow. So here if we have a very thin long plate like this one, because the front page here, the front area is very small, so means that the area of this one is not cannot give so much resistance to the airflow. So means we could assume that the drag form here, the form drag is almost 0%, but the area here, the area that parallel with the airflow is actually will give a lot of resistance, because the shear stress is actually occur on this surface, and then it will create force. So we could assume that the skin friction will contribute 100% of the resistance. So how about the aerofoil? So the aerofoil, as you know, it's shaped like this one, and the thickness of this one maybe give around 10% of the foam drag, and the area here, okay, the shear stress, the flow that flow on the surface here will give you around 90% of the resistance. So, and then if you have a circular shape like this, a sphere for example, so mean the drag form is occur because the projection area will resist the flow. So and then it will give something like 90 to 10% here. And if the same plate of this one is oriented like this one, we put it horizontally and we put it vertically. So we found that the form drag due to the surface that perpendicular resist the flow will give us almost 100% the resistance. So this is the idea. That's why in boundary layer, the example and the theoretical will given by using the idea of flat plate. Flat plate. So why? Because we want to neglect the influence of form drag. So means that the thickness of the plate is actually not give any influence of the calculation. That's why we could focus on the shear stress that occur on the surface of the plate. Okay, so what is boundary layer? So boundary layer in fluid mechanics, a thin layer of flowing gas or liquid in contact with a surface such as that of an airplane wing or of the inside of a pipe. The fluid in the boundary layer is subjected to shearing force. A range of velocity exists across the boundary layer from maximum to zero, provided the fluid is in contact with the surface. Boundary layers are thinner at the leading edge of an aircraft wing and thicker towards the trailing edge. The flow in such boundary layer is generally laminar at the leading or upstream portion and turbulent in the trailing or downstream portion. So the idea is very simple. This is the one of the experiment that showing that the boundary layer is actually exists. So the problem is we cannot see with our naked eye because there are no colors of fluid. But sometimes if in high velocity, for example, the boundary layer that occurs on the aircraft wing, because the influence of pressure, you know, when the velocity is high, so it's the air is changed from the incompressible to compressible fluid. So and then it compress the molecule of air, and then the water vapor is actually vaporized. Then we could see something like a smoke on the aircraft wing. So that's not because of the boundary layer. This is about the existence of water vapor in air that create a white smoke that could be one of the proof of the existence of boundary layer. But if we do this, so this if we just do we flow a hot air on the inclined surface like this one, and then we capture the temperature difference by special equipment. So we could see that if we found that there is a thin layer on it. So this is the existence of the boundary layer. So as mentioned here, boundary layer is actually caused by the shearing force. So this is another example. So and then normally we have just a thick a thick layer on an aerofoil. Okay, the simple idea of boundary layer is actually, I show it here. So if we have a flat plate like this one, so as mentioned in the description, we have a velocity profile. Okay, we have a velocity profile like this one, and then it is smaller at the top, and it is velocity profile is bigger at the bottom, at the rear one. So and then the boundary layer is actually another ideas about the boundary layer is the the layer is actually a real layer. It is not an imaginary layer, but what we call is a boundary layer because it is actually according to the definition. So we try to plot a locus between the changes area, the velocity changes region here, change with the region without any changes of velocity. So if we plot a border, so we take here the velocity is equal to 0, and then here, okay, when the molecule at here will have, let's say 10% velocity, we have a 20% velocity, and then it become bigger and bigger. And at this area, so for example we have a molecule here, so maybe it will have u is equal 99% capital U. So capital U means the velocity that comes from left to right here before it touch the flat plate. So and then the molecule next to it will have u which is equal to 100% capital U. So now we could draw a borderline for this on this molecule. So means we just connect here to this one and to this one. So means that in this region, the velocity is actually changed according to the velocity profile. But at this region, we found that the velocity didn't have any velocity profile. All the velocity will have the value of capital U because the molecule on this region U is equal to 100% U. Okay, so that's why we call this layer, okay, as the boundary layer. So because the layer is this layer, and the boundary means the boundary between the flow that have velocity profile, that have various velocity profile, with the region that do not have any profile, means that the velocity is constant. So this is another idea of a boundary, the definition of boundary layer. So and then I think I show it here. Okay. So as mentioned in the description, the boundary layer also have laminar and turbulent boundary layer. So for example, at the situation here, so we have a laminar boundary layer. So and then after a certain value, so it will change into the turbulent boundary layer. So and then in certain situation, there is one phenomenon called the separation. So the separation means the molecule of flow, means the molecule of fluid here. Okay, for example, we have an air. So the air here, the molecule of air is start to detach from the aerofoil. So this is the separation. Okay, so mean, and then here the changes between laminar and turbulent. Okay, we need some indicator for laminar and turbulent. So normally, okay, in if we go very specific of the uh, boundary layer, we will have a tree. For example, we have a tree region. We have a lamina here, we have a transition, and we have fully turbulent. But the transition region is very small. That's why certain textbook or in a common theory of boundary layer, we will have only two region, which is the lamina and turbulent. So to check to know whether it is lamina or turbulent, we will check using the idea of Reynolds number. So the equation is rho VL over mu. The value of L here is actually the length. So if you calculate for the aerofoil here, so it is okay for you to take the length of this one. It is not okay not to measure the length of the curved surface like this one. It is okay just to have the span length of the aerofoil. So this is the L. If the value is less than 5 times 10 to the power of 5, so we could consider it is lamina. Okay, but in certain textbook, they will give you a very specific. For example, start from 1 to 10, 1 to 9, 1 to 9, 10 to the power of 5 is actually the transition. So that's why in certain textbook, they take the transition is not worth to be studied because sometimes it's near to the laminar behavior. Sometimes it will show turbulent behavior. That's why certain researcher, they just took the simple idea, they just cut into the half of the transition area, so it's become 5 times 10 to the power of 5. So mean Reynolds number that less than 5 times 10 to the power of 5 can be considered as lamina. Okay, and if it's greater than 5 times 10 to the power of 5, so it can be considered as turbulent boundary layer. Then boundary layer also influenced by the surface roughness. If you have a greater surface roughness here, so it will create turbulent boundary layer earlier than the expected. So these numbers, this region is actually for the common smooth flat plate evaluation. So after that, in chapter 4, 5, and 6, we will see a few conditions where we calculate the transition, where we calculate the roughness, and so on and so forth. So this is actually the basic idea of the boundary layer. Okay, this is a few ideas that you need to know before we go for the next calculation of the boundary layer. First, we need to know about the three basic items for the boundary layer. One is called boundary layer thickness. The symbol is delta. And the definition is a distance from the surface where the local velocity, so the local velocity here means the small u, equal 99% of the free stream velocity capital U. So in my handwriting, I also propose to you, if you write the capital U in your final exam later on, please write as U with a bar like this. So this is just to differentiate the idea of small u and capital U, because the capital U is the velocity at this region. So means that velocity before its flow on the flat plate surface. But the small u velocity here is represent the velocity inside the boundary layer, mean at this point. So inside the boundary layer, so we call it the velocity is small u. So and then we are talking about the boundary layer thickness. So the boundary layer thickness is actually measurable. So it's what is the meaning of measurable here? So because it's real. So we could prove it in experimental works. So if we have a very clear boundary layer, so means that we could measure from here to here, okay, parallel with y-axis. So this is the delta, mean a distance from the surface, I mean the solid surface here, where the local velocity, mean the velocity of u, equal 99% of the free stream velocity capital U. So I hope you could understand the idea of 99%. Means that if we have a molecule here, so this molecule will have 99% of capital U, and the next molecule will have 100% capital U. So we take the boundary, the line is on the 99% uh, of the local velocity. Okay, so this is the idea. So if we want to express the idea of boundary layer thickness in mathematical expression, so we only could write like this one. So mean we could write delta is the boundary layer thickness. It is equal to y-axis from 0 to u equal 99% of capital U. Okay, so this is the only mathematical expression that we could derive from the statement. Because the equation is very simple, means that we cannot do more to get the value of y or to get the value of delta, unless we could measure it straightforward from the real situation. Okay, because of this, because the boundary layer thickness is very important, but we cannot calculate it by using a mathematical equation here, means that we need to create another equation to help us to calculate the value of delta later on. Okay, so means this is the first expression for the delta. So I hope you understand, you know how the boundary layer being formed. Okay, it's developed. Okay, this is the first term, the boundary layer thickness, delta. So, and then we go for the second terms, we call it as the displacement thickness. So the definition is the distance the surface would have to move in the y direction to reduce the flow passing by a volume equivalent to the real effect of the boundary layer. It is written as delta star, means delta with an asterisk mark. So we call it a star there. Calculation of the displacement thickness is done by using the idea of conservation of mass. Okay, so what is the meaning of this one? As I said previously, we have a boundary layer thickness, but the equation is not cannot give us value for delta. So mean we need to create another equation to help us to calculate the value of boundary layer thickness. Okay, before we create our equation, we must make sure that the conservation of mass is conserved. So this is the idea of physics. So, however, okay, if we have this diagram, we found that we have the incoming velocity is in a rectangular area, but when shear stress applied here, so there is no slip condition, the velocity is stuck here, so it create the not rectangular area. So means that this area is actually missing. So means that the conservation of mass from this shape into this shape is not conserved for this one. That's why we need to add an additional area. Okay, an additional area here in rectangular shape. Okay, so the length here is the capital U, but the height here is called the delta star. So that's why in the definition, it says that the surface would have to move in the direction. So displacement means we need to displace. We need to move the boundary because we want to make sure that the conservation of mass will be conserved. Okay, so according to this one, first, if we want to calculate the mass, we know that it is equal to m is equal to rho v, rho volume. So, and then for this diagram, we could have the volume is the length of u here, the height of this one, so we assume it is equal to delta. So, and then the width of this one. So because it is easy for us to calculate in two-dimensional, so we assume that the width here is actually 1 unit. So 1 unit or 1 meter, just to simplify the calculation. So it means that to calculate the mass, we just calculate the rho and the volume. So the volume is U times delta. So we get rho U delta as the mass. So means we could calculate the mass of this one, and then it must be equal to the mass of B region, this one, and plus with the region of C. Okay. So that is the idea. Okay, we could calculate like this one. So we have A is rho U delta, and MC here is very simple because it is a rectangular, so we could write as rho U delta. But for MB here, it's quite a little bit challenges because the shape is not common shape, so we need to calculate by using the idea of integration here, integral. So it starts with the idea of rho U dy, integration of 0 to delta. So we get this term. So and then here, because we have integration terms here, and this one is not with the integral mark. So, but actually it is equal to rho U delta is equal to integration of 0 to delta rho U dy. So, and then we replace this term into this one. We factorized it, and then we could get this term. So I think you could make some revision about this. And then finally, you will get the delta star can be written as this one. Delta star is equal to integration 0 to delta 1 minus u over u dy. So and then because the flow is moving at certain velocity, so we need to think about the momentum thickness. Okay, what is momentum thickness? Momentum thickness delta theta is the distance by which a surface would have to be moved parallel to itself towards the reference plane in an inviscid fluid system, a stream of velocity u, to give the same total momentum as exists between the surface and the reference plane in the real fluid. It is written as theta. So the calculation of momentum thickness is done by using the idea of conservation of momentum. So the idea is simple. First, we create equation to make sure that the conservation of mass is conserved, and then we must do something to make sure that the momentum is conserved. So if you see, the trend is the same. If we learn in chapter 1 to 3, we are going about the continuity, and then we learn about the momentum with the idea of Navier-Stokes. So and then in boundary layer, a lot of researchers start the research of the boundary layer maybe 200 years ago. So it start to calculate the continuity equation. So we call it as the displacement thickness, and then it start to calculate to make sure that the momentum is conserved. So it's produced, or it's introduced the idea of momentum thickness. So the idea of momentum thickness is the same. We just use the same diagram like this. So this is the incoming velocity. Okay, we must make sure that the momentum at inlet is equal to the momentum at outlet. So, and then to calculate the momentum, we need to multiply the mass and the velocity. So for this one, we could say that the mass for inlet is rho u delta, so the velocity is capital U. So and then for the outlet here, so we start from the simple one. So we know that the integration of this one is the mass need to be integrate, and then the velocity is small u. So and then the area here, okay. So the mass is rho u delta star, and the velocity is u, and the area that we develop for this one, for the second time, so we put the height here is equal to theta. So and then we have the mass is rho u theta, and the velocity is capital U. So, and then we could fulfill the equation, the basic idea. So mean that the momentum in is equal to momentum out. So we put everything it's here. So we could have this equation. And because we have two unknown parameter, which is the delta star and theta. So mean we need to simplify that, okay, by the idea of substitute the delta star here with the previous equation that we get. So and then we could simplify this term. And then because we want to know what is the value of theta here, so we bring the value of theta here. So and then we solve it, we could get this term. So we bring the rho u square to the right hand side, and finally we could get this term. So means that the formula or the idea of momentum thickness is to make sure that our calculation after this will conserve the momentum. So the theta here is the equation for the momentum thickness. So you will have integral 0 to delta u over u 1 minus u over u dy. So here please be careful because the small u and the capital U is two different items. So you cannot cancel it, and please make sure in your handwriting, normally I will write as u over u bar like this one and 1 minus u over u. It is just to differentiate the small and the capital U.